Okay, so VSI 3. So yeah, the geometry is going to be convenient. Normally the way we compute vector surface integrals is by saying that that ds is in du dv. And here, this is all part of our parameterization. So we're not going to do that this time. What we're going to do is rewrite this instead as f dot unit normal ds scalar, and we're going to write down exactly what that unit normal vector is, and it ends up being kind of convenient as follows. Here's your sphere. There's an example kind of like this in the section, by the way. You might want to flip through and find that. But if you have some point on the surface of the unit sphere, the outward pointing unit normal vector, note, is exactly the same as the position vector for the point. They point in the same direction because of the symmetries of the sphere, and they're the same length because this is a unit sphere, and therefore that position vector has unit length. So that n is just x. In other words, it's just x, y, z. Now that's the outward pointing unit normal. This problem here says we're looking for the unit sphere with the inward orientation. So we're actually going to be doing a variation of this where our unit normal vector is just going to be the inward pointing vector, which is just the negative of x. Namely, it's negative x, negative y, negative z. All right, so that's because, so spheres are really nice. Spheres have nice shapes, lots of symmetries and cool facts. So this lucky break here. Now, let's plug in then to this formula, and what we get is, well, let's see, f is yz, 2xz, negative 3xy. Now dot our unit normal vector, which is negative x, negative y, negative z, and we're going to do a scalar surface integral of that dot product. Well, the dot product ends up being 0, because here you have negative xyz, here you have negative 2xyz, and there you have positive 3xyz. It all cancels and you get 0. So you have to do a scalar surface integral of 0, and that's an easy scalar surface integral. It's just 0. So yeah, there you go. So I believe, let's see, I'm fairly sure that we did something similar to this in the text here. I could be confused and thinking about a different.
No, I think you did.
Yeah, it's this. So it's a lot like this example here. So yeah, why don't you take another look at this example also and compare and contrast. See, it's not exactly the same. This is a sphere of radius 3 oriented outward, so it works out a little differently, but still the point is you can write down an easy formula for your normal vector. And you can explicitly compute the dot product of the vector field, and again it ended up being 0. So yeah, take another look at that at your convenience.